Hi, welcome back to the second session of week 6. As I had told you earlier in the previous session, I intend to show you for 6 different diagrams, and I think each of them is very important and very helpful. These will become much more relevant, I think, once we do in week 7 the calculations, because the calculations, for them to make sense, you've got to have a perfect or as clear of an understanding of what the model is all about. So without any further ado, this will not really take long. Let me share with you a few of these diagrams, hopefully in order to elucidate some of the things that we have spoken about and some of the things that we're going to be calculating in the near future, which will be really next week. The first thing, before we start talking about the actual models, I would like to share with you this. I spoke to you, if you still recall, earlier about the popular theory of peak oil. Peak oil used to be a theory that was subscribed to only by very few. However, after the major oil crisis, whereby the price of oil shot up to really the almost all-time highs of 140 or 146, whatever the case might be, I forgot right now, and I didn't look it up. There were very many converts. Actually, I would say most of the even mainstream press started talking very seriously about the possibility of peak oil. What does the whole concept mean, just in case you haven't heard of it? The concept really applies to any exhaustible resource, believe it or not. Unfortunately, we don't just stop to think about the implications of what is it that goes on in the world. Now, if you notice, this is the diagram of an article that is maybe the most important article that contributed to this idea, to the spread of this idea of peak oil, and it was written by a major geologist who I believe was connected at one time with Shell Oil. The idea, however, goes back to the late 60s. There's an American geologist by the name of Hubert, and so all of these curves are referred to as being the Hubert curves. What is it that Hubert really was talking about? Well, all what he was saying, as you can see, is that whenever there is an exhaustible resource, a non-renewable resource, as you are exploiting that particular resource, you're going to have less and less and less of it that's going to be available. Eventually, you're going to get to a point at the top, it'll be like this, whereby you have already used 50% of the total availability. Then once you've reached that, that's the peak. Then every single drop or ounce of whatever the subject matter happens to be that you're going to be extracting, you're going to start having less and less and less of it. So the belief, really very simply, and it isn't much more complicated than that, is that we had arrived at a point very close to peak oil by something like 2010. Some people said 2008, some people said 2012. I mean, these things are never precise, but more or less you're saying that really we were almost at peak. Now, there are many, which really implies that oil is going to become scarcer and scarcer, and as it becomes scarcer and scarcer, what's going to happen to its price? Its price is going to go up, and that's why we had the oil crisis. Now, all of a sudden, as a result of the Great Depression the recession in 2008, the demand, industrial demand for oil all over the world has dropped, and the production of oil has increased in very many areas, and we'll talk about it briefly in a minute. And so it appears right now that the trend has been reversed. Now, you're free to take any position that you want, it goes without saying. But keep in mind that there are many economists and many geologists, and in particular, by the way, scientists who have an environmental leaning, that still believe in the validity of peak oil. Because, as we said, it's really rational. You have something that you're going to be using it, you keep on using it, you get to a point whereby you've used 50%, then everything else besides that is going to be less and less and less, and so it's going to become more and more and more expensive. And that is really one of the reasons why is it that we have to find alternatives to oil and so on and so forth. Now, Hubert, the person that really popularized this, is the person that spoke about a peak in US production in the early 1970s. And what made this so popular is that his prediction turned out to be exactly on the dot. He predicted that US and Canada, North Americans, oil production will peak in the very early 70s, and we did peak in 1973. So this, by the way, if you want to understand it a little bit better, the names, the titles over here are exactly in this order. That's to say, the top line over here is that of world, then this is the world without the Persian Gulf, then this is the Persian Gulf, then this is the United States and Canada, then after that you have the former Soviet Union, and then you have UK and Norway. But these, by the way, and that is right now the big point of controversy between those that believe in the total validity of peak oil and those that don't. This model that was drawn up by Hubert and Campbell and others was based on conventional oil. They were not taking into consideration what is known as non-conventional oil. What is non-conventional oil? Well, a very simple one, I'll give you 2 seconds to think about it, will be the tar sands of Canada. I mean, in the 1970s, nobody was thinking about the production of the tar sands of Canada. But what is the problem with the tar sands of Canada, as we spoke about this morning, is that yes, they are there and they can be exploited. However, in order to do that, it's going to be very expensive because there isn't very much net energy. That's to say, in the 1970s, when oil was selling at $10 or $12 a barrel, nobody was thinking about using the tar sands of Canada, or even some of the heavy oil of Venezuela. Venezuela is extremely rich also in oil, but most of its oil is heavy oil, so that is more expensive to extract, and it takes much more in order to refine it. And so again, what do you wind up with? You wind up with less net energy. And the idea, as we said earlier, is that you will get to a point whereby you will have a lot of non-conventional oil, but it wouldn't be feasible to go ahead and extract it because it wouldn't have any net energy. An excellent example, by the way, and I don't want to digress, but now that we've mentioned the term a couple of times, will be the ethanol. I mean, there are many studies that have suggested over the years that the ethanol at best really has a net energy of under 10%. And there are many studies, by the way, that actually argue that ethanol does not have any net energy. Actually, it is an energy sink. That's to say, once you take into consideration all the energy that is used by the farmers in order to grow the corn, in order to harvest it, in order to go ahead and change it into ethanol, and by the time that it gets to the gas station and you fill it up, all of that energy will be that's going to be needed will be greater than the energy that you get out of the ethanol. So there are a number of examples that really show the limit, and that, by the way, is one of the reasons why is it that there hasn't been that much demand. Had it not been for the congressional mandate, then most probably the market would not be using corn right now as an ethanol, at least not in the United States, because the economics and the net energy really do not warrant it. So, one more time, all what this is showing is that yes, there is going to be a peak, no doubt about it. If it's an exhaustible resource, there must be a peak. The only question is that when is the peak going to happen? Is it going to be in 2010, 2020, 2025? You have all sorts of explanations right now by all sorts of different people, but there is no doubt that we are either at the peak or very close to the peak, even when you take into consideration the non-conventional. Because if you take away the non-conventional, yes, there was a peak. And without the non-conventional, we'll have tremendous oil shortages right now, and therefore the system that we have built in the world over the past couple of hundred years will not be able to survive. The economic system that we have requires much more energy than we are capable of supplying through conventional oil. And that's why we had to find these marginal, the non-conventional are really marginal. And this, one more time, by the way, brings back the issue about fracking. There are American geologists that argue that if fracking is to be adopted all over the world, all over the globe, then the peak will be pushed further by, let's assume 50 years or maybe even a century. Because we know what's happened to the United States. The decline in 1973 has been reversed, and has been reversed only as a result of fracking. And I don't want to get into it right now, but as you well know, those who are opposed to fracking, they point out to the downside. Because fracking, just like everything else, in economics, there is no such thing as a free lunch. And so it makes certain demands on water, on the water table. Some people are even making accusations that it causes some earthquakes and what have you. But we cannot keep on using the oil, whether conventional or non-conventional, at this rate without running into problem, which is, one more time, it shows, as we were saying earlier, the need to go ahead and move into a renewable, and to move into a renewable as soon as possible. Now, I want to show you something else right now that is very similar in essence, speaks about the same issue, but in a slightly different manner. This is probably the best potential supply curve of oil in the world, which really again speaks about the same thing that we have been talking about. Notice what we're really saying over here is the dollars per barrel, the price, and over here the type of oil. Now notice, for example, that OPEC in the Middle East and certain other OPEC countries will be produced at a profit for under 20, over here under 10, and over here under probably say 27. Other conventional oil can be also produced up to around 30. But the non-conventional, as you can see, they will never be produced at these prices. The non-conventional require a much, much, much higher price. I mean, some of them, in order to really make sense, they will have to go up, as you can see, according to this, which is already probably around 7 or 8 years old. But so right now, that means that right now probably the prices are even higher, is that you need 130. I mean, what people are suggesting, by the way, is that, okay, so we move from oil to natural gas. That is going to be obviously the easiest and the cleanest, and as a result of fracking and the availability of natural gas all over the world, it is the best transition fuel. But what do we do after that? After that, I think what we're going to do is that we have to move into the other non-conventionals. Because as we go past peak in conventional and in natural gas, then we'll have no choice but to go into the tar sands. Once we go into the tar sands, there aren't really that many tar sands outside of Canada and maybe one or two only other places in the world, and the heavy oils of Venezuela. And then we'll have to go into shale. And shale is really rocks. You've got to go ahead and you mine the rocks and you heat the rocks so that you will get oil out of the rocks. And that will be extremely expensive. In the United States, we tried that during the time of Jimmy Carter back in 1978. And then we found out, because Colorado is one of the richest places in the world with that kind of a rock. But then you will be mining oil. And the damage, the environmental damage, will be simply tremendous. And the demand for water that is already scarce all over the world will be great. And this is also, by the way, one of the shortcomings of the tar sands. So as you can see, if the demand of oil in terms of quads, of energy, to go back to the diagram that we looked at in the previous session, if our demand for energy is going to become, say, 120 quads, and the world demand is going to become 700 quads, where are we going to get it from? It really doesn't exist, except to go to the non-conventional, and that will be disastrous. And so, one more time, you'll have people who are arguing that there is no need for any more growth, because we cannot really keep on growing at this particular rate. And it becomes the same argument that we have sort of touched upon here and there. Now, if you are convinced of this, and I hope that you are, then what do we have to do in order to model these? Well, the first is going to be this. If you have a particular exhaustible resource, then all what you have to do is that you assume that you're going to be extracting it until you run out of it. We don't know when. Say maybe in 100 years, in 200 years, in 1,000 years, whatever. It depends on the rate of consumption of that particular resource, and it depends on the availability of that resource. But as you can see, you will start extracting. So this is not a demand curve. This is an extraction curve. It shows you how much you extract over time. So in, 100 years or 1,000 years, you would have used all of this. If this is the case of an exhaustible resource, let's call it oil. So we found oil, we know how many billions of barrels we have, and we're using them. Eventually, we're going to run out of them. What's going to happen to the price? Well, over here, we can really predict at least the shape of the price. We're going to assume that there is a marginal cost of extraction. This over here is the marginal cost of extraction. And we're going to assume, just for simplicity, that the marginal cost of extraction is constant. That's why this is a horizontal line. But what about the price? Well, as probably all of you should know, but just in case somebody doesn't, we've reminded you of that earlier. Eventually, really, the marginal cost determines the price. So you can think of this as being really what the cost curve. So what's happening to the price? The price is increasing and increasing and increasing and increasing. Why is the price increasing right now? All of us should be able to answer this. That's why I wanted to go through this so that it become very clear in our mind before we start doing the exact calculations. Because of rent. So this is rent over here, MUC. What happens to rent? I hope, again, all of you have answered this correctly based on the numerical examples that we have solved and the example that's given in the book. Over 2 periods, we find out that price in period 2 is higher than the price in period 1. Why is it higher than the price of period 1? Because the rent would have increased at what rate? It would have increased at the discount rate. So as you can see, one more time, the discount rate is included over here. It isn't the price that increases at the discount rate. It's the rent that increases at the discount rate, and then you add to that the constant marginal cost. Depending on the kind of model that I want to share with you next week, but what will be one way of really simplifying this? It would be to assume that marginal cost is 0. If marginal cost is 0, then this model becomes easier, because then the increase over here in the rent will be the same as the increase in the price. Otherwise, you will have to add this to the rate of increase in the rent. But some people might object to this by saying, okay, this is a resource that is exhaustible, that is non-renewable, and then we run out of it. And this is what's going to happen. You see, by the time we run out of it, if this is 1,000 years, over here in 1,000 years, this is going to be the price. Because this will be the marginal cost per unit, per ounce, per kilowatt hour, or whatever it is, and this is going to be the rent. So the price is made up of 2 components, of the marginal cost of extraction plus the rent. Now, to make this a little bit more realistic to what is it that you and I are interested in, especially when it comes to the question of oil, we're saying, wait a minute, we have a resource that is exhaustible, but we're trying to replace it with something, with another one that is renewable. So in this case, we're going to extract the oil at one rate up until this particular point. At this point, what do? We will replace it with a renewable. So this is where so we will have right now a very smooth transition without a crisis. So if we're going to have a smooth transition from oil into a renewable, we will go down like this, and then we will replace the renewable. So all of a sudden, we're going to stop extracting that particular oil, or whatever that commodity is, but we're assuming that it's oil. What do we assume about the cost? Is that there was a marginal cost of extraction. Because of scarcity, then there's going to be a rent, an MUC, and so that price is going to go up. This is going to be the total price right now. This is going to be what right now once we shift into the renewable. So the price right now is no longer going to increase, it's going to be like this. And that, by the way, as you might expect, would be the case if it so happens that, say for the sake of the argument, and I know it's not going to happen, if we can shift, let's assume, in a year or two from oil into, say, solar. So in that case, this will be the profile of the extraction of oil and the price that's going to be over here, the price of energy. However, some people will argue, what if we're going to move from one renewable resource into another renewable resource? If I'm going to move into another renewable resource, then this will be the case. So I will move into one renewable resource with an increasing marginal cost, and then I will move into another renewable resource. And I could, by the way, move into a third renewable resource for that matter. But it is possible, therefore, to have all of these possibilities. I was going to show you a fourth one, if I can find it. Oh, here it is, okay. The fourth one is probably the most realistic, but obviously if you're going to do any calculation, since we're doing them by hand, we're not using computers or any programming or whatever, then it becomes a little bit more difficult, because we're going to assume in this case that the marginal extraction cost increases. As the marginal extraction cost increases, once you shift into the renewable, as you can see, you will get to that particular point whereby this will be the cost of the renewable. If you're going to look at these, and by the way, try to relate them. Let's assume that you're in charge of Saudi Arabia. What is this really saying? And take it from me for a fact that essentially these models, obviously a little bit more sophisticated, they're not linear and what have you, but these models are the ones that are being used by Saudi Arabia, by all the Persian Gulf countries, by all the major producers in order to determine the price and the switch point. These are referred to as the switch points. This is where you switch from one to the other. The important thing, if you were Saudi Arabia, is not to allow the price of oil to become so high as to force consumers to stop using oil, because then they will switch into a renewable. So Saudi Arabia would like to keep the price of oil below the switch point. Let's assume, for the sake of the argument, that this switch point to a renewable is $75 a barrel. Then Saudi Arabia will do whatever it takes to keep the price of oil below $75, because it doesn't do Saudi Arabia any good for the price of oil to become 100. Because what will happen if the price of oil is going to become 100? Definitely Saudi Arabia is going to benefit during the first few years. But that is what's going to happen eventually? Eventually we're going to stop using oil totally, because we would go ahead and switch totally into a renewable, and Saudi Arabia will wind up with oil in the ground. So they will have all of these assets that are expected to last them for 300 years at this current rate, whereby they wouldn't be able to sell a single drop of them. And so obviously, one thing to understand about the current pricing structure, why is it that the price has dropped so much, is that Saudi Arabia decided that it is not in its favor for the price of oil to stay, let's assume, at 100 or 150 or whatever it is. Eventually, in, I know, a couple of decades or whatever it is, if the purchasing power of the dollar really drops, then yeah, that's a completely different story. But right now, given what we know, a high price will imply that we're gonna switch, and the switch is very bad for Saudi Arabia. So Saudi Arabia, notice right now, if you are an environmentalist, Saudi Arabia has no interest in environmentalism, the way that it is currently structured, because probably 80 or 85% of the government revenue comes from oil. And they have enough oil reserves for the next 300 years. So right now their policy is to be able to use as much of that as possible. They don't want the oil to just stay in the ground. Therefore, they've got to maintain a switch point that is a price that is lower than the switch point. We'll try to work some numerical examples about this next time. Okay? So I'll see you next week, whereby we'll do 2 or 3 numerical examples.